Okay, so like I said, this is the last formal video lecture, Zoom meeting, class recording, whatever you want to call it. This is the last full formal one. Okay, and so obviously we'll go through our lecture like usual, and since this ends the last week of our meetings, I'll obviously make a special announcement at the end of it to make sure that everybody is good to rock and roll here. All right, so let's get into it. Obviously, we are in Algebra 2, and yesterday we finished Unit 4, okay, and we were able to do one lesson in Unit 5, so we were able to introduce right triangles, okay, and so today, if we can, we'll try to go through 5.2 to 5.4 if possible, all right? If not possible, of course, that'll just turn into a weekend assignment there for us, okay? So eye on the prize. All right, so looking at 5.2, we're going to talk about angles and radians, okay? Angles and radians. All right, so angles can be defined as two rays that meet a given point, all right? And again, a ray is a line with a direction, okay? And basically the measure of the angle can be in either terms of degrees or radians, right? I know all of us are familiar with degrees, but we might not remember radians here, all right? So this is the formal definition of an angle, okay? So this is an example of a ray, all right? Because it's got a arrow here, it's got a direction, and it's saying if you have it starting at the same point and you have another ray and it goes out, great. All right, so we label this endpoint with a letter, right? With any letter, and they used a capital A there, okay? So all of the ending points make up this angle, okay? So right now, since there only is one point, we would call this angle A, right? And that's what that little symbol there means, is angle, okay? And it's larger, like significantly larger than a greater than or equal to sign, right? So it is larger, even though it does look similar to like our less than or equal to signs, okay? But if we put points on this, right? So if we actually give this ray definite points, right? So we turn this from a ray into maybe like a line segment. So imagine we cut off the ends of this ray here, okay? We can now label this as BAC, angle BAC, because it goes from B to A to C, or you could have also said CAD. Both of those are fine, as long as you have the letter A in the middle, because obviously it goes in the middle if you're tracing along this line here, okay? So that's just a quick introduction to angles here, all right? And so, of course, the first thing we've got to look at is the different types of angles, okay? The different types of angles. And we are dealing with a perfect circle here for right now, for example. So if we look at our different types of angles, so there's this one called an acute angle, all right? And acute means 0 to 90, right? So it's an angle that's less than 90 degrees, all right? And I think the way that I was told it is oh, look, it's a little cute angle, like something along those lines if you need help with that, all right? Obtuse, okay? Obtuse means you're greater than 90, but less than 180, right? So you're gonna be over here in this quadrant 2, right? You're gonna be over here in this quadrant 2, all right? And then reflex angle is anywhere between 180 and 360, all right? And again, the way I look at this is like reflex, it kind of looks like it reflects maybe, I don't know. However you wanna remember these, all right? A zero angle is where it has the two rays on top of each other, right? So both of these lines are on top of each other. So that's a zero angle, all right? And then last is a straight angle. So that's perfectly 180, right? That's a completely straight line as long as you notice that there's two different line segments, okay? So this is our 180 or our straight angle, okay? So then looking at this here, like I said, anything that's less than 90 is going to be acute. So I'd go through anything less than 90, I just look for, and that makes it acute. All right. Then obtuse is anything between 90 and 180. All right. So I pull all those. And then, of course, reflex is anything greater than 180 and less than 360. Okay, so between 180 and 360 is reflex. All right. So again, you can go through this and try this on your own, but those are what the answers are going to be. Anything less than 90 is acute, 90 to 180 is obtuse, and greater than 180 is reflex. Okay. And so then there's a way, and I mentioned this to my juniors when we looked at this earlier, that I've never talked about this a whole ton here. All right, so it's something that I find interesting, and it's called the degrees, minutes, seconds. All right, so there's a way of expressing things in terms of this degree, minutes, seconds. Okay. And basically what it's doing is it's taking a decimal, right? So instead of saying 5.25 degrees, it's going to turn that 0.25 into this minute and seconds, right? Into this minute and seconds. All right. So kind of nifty. All right. So if we watch this here together.
In an entire circle, there are 360 degrees. If you start with the 0 angle and then draw more rays with endpoints on the circle, you will be drawing angles that increase in measure from 0 degrees all the way to 360 degrees.
Okay, so if we were to start here, go all the way around, that would be our 360, right? So we're going to draw and we're going to go 0, right? We said 90, 180, 270, 360. Okay, so inverse clockwise.
What do you do if the measure of an angle is not an integer? You use the same approach that you take when measuring linear distance. You might say, for example, that something is 15.75 yards, or you might say that it is 15 yards, 2 feet, and 3 inches long. The same thing is done with angle measure using degrees, minutes, and seconds. To do this, you need to know that 1 degree equals 60 minutes and 1 minute equals 60 seconds.
Okay, so again, it's another way of expressing, but in different units. So again, same thing, like they have, you know, it's 10 yards, 3 feet, 5 inches, right? It's going to be the same thing. We're going to talk about degrees, we're going to talk about minutes, and we're going to talk about seconds. So again, reminder, he said the important thing is to know that there's 60 minutes in 1 degree. Okay, there's 60 minutes in 1 degree, and there's 60 seconds in a minute. All right. So keep going there.
Suppose, for example, you have an angle that measures 20.32 degrees, and you want to express this measure using degrees, minutes, and seconds. How do you do this? You know that you have 20 whole degrees plus 0.32 of a degree. How many minutes would 0.32 degrees be? Since there are 60 minutes in a degree, you can find out by multiplying 0.32 by 60. This tells you that you have 19 whole minutes plus 0.2 of a minute. Then, since there are 60 seconds in a minute, you can find out how many seconds are in 0.2 minutes by multiplying 0.2 by 60. Now you know that 20.32 degrees equals 20 degrees, 19 minutes, and 12 seconds.
All right. So again, to walk you through those steps, what he did was he took this 0.32 degrees. All right. He multiplied 0.32 by 60 because there's 60 minutes in 1 degree. Right, so since this is a fraction of a degree, we're going to multiply it by our 60 minutes, okay? And this is going to tell us we have 19.2 minutes, all right? And again, since we have a leftover here of 0.2, we're going to take 0.2, and we're also going to multiply it by 60, all right? We're going to take 0.2, and we're also going to multiply it by 60, all right? And that gets us this value of 12. So again, as he wrote it, 20 degrees, the degree symbol is that little like oval or that 0. Okay. 19 minutes, that's just 1 apostrophe. All right. And 12 seconds. So there's 2 apostrophes. All right. So again, notation is going to be very important, making sure you understand that. And then obviously minutes comes before seconds, so you would write it as such.
You can check your work by going the other direction. If you start with 20 degrees, 19 minutes, and 12 seconds, you can reason this way. 12 seconds is the same as 12 3600ths of a degree, because there are 60 seconds in a minute and 60 minutes in a degree, so there are 3600 seconds in a degree. 19 minutes is the same as 19/60ths of a degree, because there are 60 minutes in a degree. When you do this calculation, you obtain 20.32 degrees.
Okay, so that's another way of doing this. All right, that's another way of doing this in the reverse direction here. Right, so taking 19 and dividing by 60, taking 12 and divided by 3,600. Geez Louise, sorry. So then just putting it together, right, adding it all to the original 20, and that's what we get here. All right, so having these kind of relationships is going to be very, very important and make these calculations super easy for you. Okay. So again, I'll let you guys try this one here on your own. But remember, you're dealing with degrees, and it's asking you to convert into this DMS, which again stands for degrees, minutes, seconds. All right, so if I do this first one here with you, and I'll write down, I'll try to annotate as I go what I'm doing, okay? So the first one is asking you for how many degrees there are. So there's 55 degrees, that's a whole degree, all right? Then we have 0.45 of a degree, all right? So what we have to do is we have to convert that into minutes. And so I'll type in minute conversion. I'll make it into an arrow. All right, so we take 0.45 and we multiply by 60. All right, and when I plug that into my calculator, that gives me 27. So that's like saying there's 27 minutes. And since I don't have a decimal left over, that means there are 0 seconds. All right, so that's what I'm going to write as my final answer here. All right, so if I go and I look here, this is 55 degrees. This 1 tick mark means minutes, so 27 minutes, 0 seconds. And this angle is about 55 degrees. So that makes this an acute angle. It's less than 90. All right, it's less than 90. All right, so that's all I did here. All right, same thing. If I go to do one more here, oh gosh, I go to do one more here, so I leave one for you, okay? Obviously, there's 134 degrees, all right? And then we take our 0.26 and we multiply that by 60, and that gives us out a value of 15.6. So what this tells us here is we have 15 minutes. All right, and then we take that 0.6 and we multiply it again by 60 in order to get our seconds. So 0.6 times by 60 gives us 36 seconds. All right, and all I'm doing here is just following through with that process, right? So 134 degrees. We've got 15 minutes. We've got 36 seconds, okay? Now this angle is between 90 and 180, so it's going to be obtuse, right? It's going to be that obtuse angle, all right? And so you guys can go back through and try those. Obviously, you have to try those first ones for yourself to even get to this point here, okay? And this point, is asking you to work backwards, okay? So now you're being told what the notation is in degrees, minutes, seconds, and you're being asked to go through these. So again, 27 degrees, all right? And we've got 32 minutes, okay? So as you saw on that little video recording, you're gonna take 32 and divide it by 60. And what that's gonna give us here is a 0.6, okay? So we have 0.6. Then we take our 51 seconds and we write that as 51 divided by 3,600 because 60 times 60 is 3,600. All right. And if we do that, we get out a value of about 0.014. All right. So then if we add those together here, right, we add them together. We've got 27 plus 0.6 plus 0.014. So if we add them all together, let me get that in my calculator here. All right. So, oh. All right. So then we're left with an angle. Hold on, hold the phone. There we go. We're left with an angle that is 27.61 approximately, if we were gonna round this to 2 decimal places. And what this guy is it's 27, so again, it's another acute angle. All right, I wonder what they're wanting here. So let me double check to make sure I've done my math correctly. 36 divided by 60, awesome. 51 divided by 3/6. Yeah, so I have that as my answer, so I wonder what they're looking for. Huh. Interesting. So I'm not quite sure how they got to that value here, unless my calculator's freaking out on me. But that's how we do this conversion. We take 30, oh, because I'm a dummy. Miss Judy's so dumb. Oh, I can't believe none of you stopped me. I'm sorry. It's a 32 there. I even wrote over here, I wrote 32, and then I still typed in 36. So again, of course, ladies and gentlemen, I am only human, so to err is human. And clearly that's a pretty big one there. So sorry, a little embarrassing. All right, but you get the point, right? Essentially, you would plug them in, use the divided by 60 or divided by 360 rule, or sorry, 3,600, and you should get these added up together. As long as you can tell the difference between a 2 and a 6, I think you'll be fine there. All right, so again, give those a good shot if you can, for some extra practice there. Okay, but now what we're going to talk about is we obviously talked about degrees, and we talked about another notation known as degrees, minutes, seconds, but then we've got to talk about a major one here, which is this thing called a radian. All right, so it's a radian. And again, it can measure angles. All right, it can measure angles. So again, a circle is divided into 360 degrees. All right, 360 degrees. And each circle is what we call 2 pi. Okay, we call 2 pi. And again, the reason that is because the circumference, right? The circumference formula for a circle is 2 pi r, right? That's 2 times the pi times the radius. Okay, so when we're dealing with the angle here, in general, or sorry, that's the area equation. So, but in general, that's talking about 2 pi being the entire circle. All right. And radius, the radius of a circle is from the center point to the edge of the circle, right? So that would be talking about its radius, all right? So if we look at this here, all right, if we look at this, it's asking what is the measure of this in radians? Well, it's 30 degrees, so what's 30 degrees in radians here? And we'll look at that and talk about it, okay? So we can use our proportional reasoning that we're so great at now, okay, to investigate this circle here. All right, so what we can say is we know that it was 30 degrees is the angle that we're looking for, all right, and the entire circle was 360, all right. We were looking for our angle theta in radians, and it was over our entire circle of 2 pi, right? So this is a proportion. It's going to be the same, right? Regardless, it's just one's expressed in degrees and one's expressed in radians, okay? So if we do some simplification, we get to 1 over 12, right? If we do some rearrangements in order to isolate our theta here by itself, we're left with 2 pi over 12. Again, we do another simplification, and we're left with theta equals pi over 12. Okay, theta equals pi over 12. All right, so again, we can do this every single time if we'd like to. Or we found a shortcut here where in order to go from degrees to radians, right? So if we are in degrees and we want to get to radians, we can multiply by this factor of 2 pi over 360. Or if we want to go from radians to degrees, we can multiply by 360 over 2 pi. Okay? They're the same values. It just depends on which one's the numerator and which one's the denominator. Right? Which one's on top, which one's on bottom. All right? And a trick for you there is, in order to have degrees, you need to have degrees in the numerator. Okay, you need to have degrees in the numerator. That needs to be the thing left on top. Okay, so you can look at this here. All right, beautiful. All right, and so we can do that conversion there. And the reason it's asking you is why can you reduce this to a simple fraction? Because if we look here, if we get rid of this 30 and we bring it over on this side, we bring our 2 pi up, it's 2 pi over 360, right? It's 2 pi over 360. And again, that's how we were asking to get from radians to degrees. That's our equation right there. And if this scenario was flipped, right, and we were trying to solve for our degrees here, we would just multiply our 360 up. So again, it would give us this other equation. So that's essentially why we can do this, is because of these proportions that we now understand. All right. Looking at our definition of a radian, again, I told you area of a circle is 2 pi r, right? 2 pi r. And r is, of course, this thing called the radius. All right, it's called a radius. All right, and if we have an angle of 1 radian, all right, so again, if we have an angle, and this is exactly 1 radian, all right, at 1 radian, the curved part is equal to our smooth part, or this is called an arc. So our arc is equal to our radius. Okay, our arc is equal to our radius. And again, it's this thing of 1 radian, right? It's this thing of 1 radian. Okay, so then, of course, looking at radians and degrees, we now understand a little bit more about that conversion factor. So again, let's take a look at this this understanding here.
Because the circumference of a full circle is 2 pi, the circumference of a half circle is pi. Thus, there are pi radians in 180 degrees. Using your calculator, you can approximate 1 radian to be 57.3 degrees. To convert from radians to degrees, multiply by 180 over pi. To convert from degrees to radians, multiply by pi radians over 180 degrees. Keeping the units in mind, you can see that these formulas will be easy to remember.
Okay. And this is something that I'll walk you through here. It's called unit cancellation. Okay. So again, my juniors already know about this. It's called, or we also called it dimensional analysis in chemistry class, but it's a really nice way of looking at it. Because if you have radians, and we know we're trying to get to degrees, if you write out your units here, right? If you write out your units here, right, we can convert this. So if we know that we have 2.34 radians, and one of the conversions they said is 180 over pi radians, right? Or we also have that 360 over 2 pi, right? Either one of those will work, all right? But if you look here, radians on top, radians on bottom, those are gonna cancel each other out, right? Just like they would if they were an X value. You have one on top, you have one on bottom, you cancel them out, right? So we're left with, once we do the math and actually multiply by 180, divide by pi, right, we're left with a value, and the only unit we have left is this degrees. Okay, so we've essentially converted from radians to degrees there. Same thing when we go from degrees to radians now. All right, we start with the symbol of degrees. We have degrees on top, degrees on bottom. Those guys cancel each other out. We actually plug it into our calculator, and we get out approximately this 1.31 radians. Okay, so that's a way of looking at that as well here. All right, it's a way of looking at that as well. All right, so I will let you do this on your own here. Oh, actually, I always say that and then I help you through it. So let's just take a look at it here. Okay, so if we look at some of the key points of a circle. All right, again, we start at 0, we go all the way to 360, or we go from 0 radians to 2 pi, all right? So therefore, we know right now we've got 0 and 360 degrees, okay? 0 and 360, those are some major points there, all right? Other major points that we talked about was 180 degrees. So we just said that since that's half of our circle, that's gonna be half of our 2 pi. Right, that's going to be half of our 2 pi here. Okay, so that's at 180. Now, half of 180 is 90. All right, half of 180 is 90. So take pi, divide it by 2. That's how we get to 90. All right, so pi over 2 is going to be our 90 degrees. All right, halfway between pi and 2 pi is 3 pi over 2. Right, it's this 3 pi over 2, right? So if I go halfway between 180 and 360, I'm at 270, all right? Again, I know I'm going quickly, so take a minute when you get home or when you are off this meeting to actually go through this yourself if you'd like, okay? So there we are so far. Now, let's go back to this 90 degrees here, okay? So if I go 90 degrees and I take that in half again, like 90 divided by 2 gives me 45 here. So all I have to do is pi over 2 divided by 2. So I'm going to be left with this pi over 4 value. All right. And again, you can use deduction, reasonable analysis. You can actually do conversions, whatever you want. But a value that's between 0 and 45 is this value of 30. Right? It's the only value that could fit there. Same logic goes for this pi over 3. It's got to be between 45 and 90, so it's going to be this value of 60. Okay, it's going to be this value of 60 here. All right. Now, 2 over 3. All right, 2 over 3. That's like saying 1 and a half, right? Oh my gosh, no, it's not. It's 2/3. Sorry, it's 2/3. It's 2 pi over 3 there, okay? And so if I look though, it's like saying pi over 3 multiplied by 2. So we take this pi over 3 here and we multiply by 2. So 60 times 2 gives me 120. All right. Same logic here. I have 5 pi over 4. 5 pi over 4. All right. So if I go here and I go from 4 pi over 4 here, that's 45. So this is saying 5 times that amount. So 5 times 45 gives me this 225. All right. And then lastly, I'm left with this 11 pi over 6. Right. So again, if I look over here at pi over 6, it's 30 degrees. If I multiply this by 11, I get 330 degrees. All right, and you can go through and we can check, but essentially it's all going to work out here. So again, understanding the relationship between these, knowing how to calculate whatever it is that you like to do, go ahead and look at that. All right. And so then, of course, we've got to talk about practical things. And I love that they included it here. So on your calculators, on your graphing calculators, okay, it's going to make a difference when we start talking about degrees versus radians. It's going to make a difference what mode your calculator is in. All right, especially if or when we start dealing with sine, cosine, and tangent again. All right, so that's going to make a huge difference. So you need to make sure that the mode button on your calculator, it's usually right up here, somewhere near the top, okay? It says mode, and if you click on mode, somewhere on there it will say radians or degrees, right? It will highlight radians or highlight degrees, okay? So obviously you need to make sure that whatever value you're dealing with is the one that your calculator is set to, okay? So you need to make sure that you change it to the correct thing, so that when we go to here, you can go tangent of 45 degrees. So you type in your calculator and it will know that, hey, I'm dealing with degrees, because tangent of 45 degrees is a way, way different answer than radians. If you're using your calculator, this would give you an answer of 1 if you're in the correct degree mode. If you're in radians, it'll give you an answer of 1.61, which is obviously incorrect. Okay, so you need to make sure that your calculator is in the correct mode for it. All right, and then going back to, again, with this arc length. Okay, going back to this arc length here, we now understand what a radian is, so we can actually start to calculate the arc length, so the length of that curved part of our circle.
Consider a circle of radius r. The central angle theta, measured in radians, determines an arc of this circle. How long is the blue arc? The length of an arc is defined to be r times theta, where theta is the measure of the central angle in radians.
Okay, so
for example,
all right, so again, arc length is going to be our radius times by our angle. All right, our radius times by our angle. All right, and then of course they said a special case is if our radius is 1. All right, if our radius is 1, then it's going to be an arc length of just theta. All right, and then we'll talk about a special circle of radius 1 later on.
For example, if you have a circle of radius 5, and if theta equals 3 pi over 4, then the corresponding arc length is 5 times 3 pi over 4.
Again, plug it straight in. It's just a pretty simple equation here, right? You take your radius times by your angle, as long as it's in radians, right? So again, it has to be in radians. We multiply that out and we get our value. Okay, so again, it has to be in radians. And again, that squiggly line means approximately, so obviously it was a larger decimal and they had to round it there. Okay, so then here earlier in the intro, there was a talk about a Ferris wheel. All right, so again, if we look at this Ferris wheel being our circle, right, we can look at the radius of the Ferris wheel being from the center to each of the little carts, okay, or cars. It's 25 feet there, right? So we have a radius of 25 feet, all right? We figure out that there's a 30-degree central angle, all right? And it's asking you how far will you travel by the time the car reaches your position, or the position where your friend is at that 30-degree angle. So if I'm here and we're going up, by the time I get there, how far have I gone? All right. So again, we know it's a 30-degree angle, but in order to do arc length, we said we need to convert to radians. Okay. So what we can do here is we can do our conversion. So this is where you've got to remember which formula. So I've got 30 degrees. So I need my degrees and my degrees to cancel. So I need my degrees in the denominator. All right. And so then I'm going to be left with pi over 6 radians. All right. Then what we can do here is we have our arc length equation. And our arc length said our radius 25 times by our angle in radians gives us, I believe the value is, oh, sorry, there you go. Right, I didn't plug it in my calculator, but if I had, the answer would be 13.09. Okay, so we can say by doing this simple process here that we would have traveled 13.09 feet along that arc. Okay, along that arc. All right, so lots of good things here to remind ourselves, and you guys can take a look at that. There's a lot of, like I said, there's a lot of things that we talked about here, so you can do this on your own, but as a quick, fresh reminder here, we said an acute angle is between 0 and 190, all right? A central angle is an angle whose vertex is the center of the circle, okay? Obtuse angle is measuring between 90 and 180. A reflex angle is 180 and 360. All right. A second is 1/3600th of a degree. All right. A minute is 1/60th of a degree. All right. A zero angle is an angle measuring zero straight angle is measuring 180, and then a radian is used as this 180 degrees over pi, right? So that's how we can say what a radian is. It's 180 degrees over pi. All right. So again, that's just a really quick summary of everything that we've learned here. Okay. So again, you should be able to convert from radians to degrees or degrees to radians. You should be able to do an arc length calculation given the radius and the angle. Right, whether or not you have to convert that angle is up for debate, right? But you have to do that. Okay, and then you have to solve for this missing angle in terms of radians. Okay, so you would use one of your inverse functions, right? You could use your inverse function to figure it out. Or again, what this is saying here is knowing what that angle is and then doing a conversion to radians. Okay, so knowing what that angle is, converting to radians. All right, looking at our study guide here, of course, again, we went over what makes an angle using these ray points, knowing how to label our angles, so P and M or M and P, right? Both of those are fine. Identifying the different types of angles, again, identifying, being able to convert into this degrees, minute, second form. Being able to go back and forth between that is going to be important. Understanding radius and arc length, and again, really how to convert back and forth from degrees to radians, right? And understanding this essential relationship between some major points on the graph here. Okay. Again, ultimately, it goes back to understanding and applying. All right. With the checkup here for this little section, of course, we're going to talk about labeling angles, right? Again, if the angle theta, right, and is there, and you notice, obviously, it's also got that little symbol connecting the two rays. Okay, that's indicating that that's the angle we're talking about. Okay, so it's not this one out here. It's obviously this one in the middle. Labeling those, again, conversion to and from degrees, minutes, seconds, converting from and degrees and radians, and then indicating arc length. Okay, so pretty standard, straightforward, I hope. Okay. of course, there's a quiz with this one. And again, I'm assuming it's going to mock exactly what you see in the checkup, exactly the order. All right. So there should be no surprise there as to what you're being asked. All right. And now what we're going to do is we're going to go over trigonomic ratios and this thing called the unit circle. All right. And yes, we do have 2 studies on it quickly, but hopefully not too terrible here. Okay, so again, we'll look back at our trigonomic functions, that sine, cosine, tangent, cosecant, secant, and cotangent. All right, so we'll look at that. All right, and then we see these functions, okay, it's a repetitive motion. All right, just like this person bicycling, it is a repetitive motion. All right, so again, reviewing our functions, I'll let you guys try that, but again, we're talking about SOHCAHTOA. Right? Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. Tangent equals opposite over adjacent. Right? And I can even write that down for us here just to keep it fresh in our mind. Right? SOHCAHTOA. All right? And then understanding that there is a relationship between sine and cosecant. There's a relationship between cosine and secant, and there's a relationship between tangent and cotangent. All right. And again, the relationship is that these 3 here, secant, cosecant, and cotangent, those are all inverses of the original function, right? So this is 1 divided by sine. This is 1 divided by cosine. I guess I should put an equal sign there. There we go. Okay. Equals 1 over tangent. Okay, so all of those are right there. All right, so that's what those relationships are in terms of this review here. You guys can go through again, of course, do that activity. But now we're going to deal with this thing called the unit circle. All right, and so what the unit circle is it is essentially just a circle with a specific radius of 1, right? It's got a radius of 1, all right? And so that was that special case that we had introduced in the last unit here, all right? So again, a unit circle is just a circle with a unit of 1, right? A radius of 1.
Starting at the right side of the unit circle, move along the circle t units to the point P. This is called the terminal point. If you draw a straight line from the origin to the terminal point P, you create angle theta. Remember that by measuring the angle in radians, you can easily relate arc length t to the measure of the angle. If you draw a vertical line down from point P, you form a triangle with angle measuring theta radians. With the definition of sine and cosine based on the unit circle, you can now redefine all 6 trigonometric functions.
Okay, so let's take a hot second back here and re-talk about this, because I know she flew through that. All right, so again, this is our unit circle. So it's got a radius of 1, so it goes out in 1 in all directions, okay? And it's having this angle, right? Of course, we always start at this original 0 point, okay? And it's going up to this angle, which we call P, right? And if you guys can remember, obviously this is a coordinate, okay? So this right here is a coordinate x comma y, right? So this is a coordinate, an xy pair here, all right? And again, we know that t is our arc length, right? And this is that special case that we said where if we have pi times radius, our radius is 1. So this arc length is just equal to our angle in radians, okay?
If you draw a vertical line.
So then, of course, they're talking about, she said, draw a vertical line. So we're going to make this into a triangle here, all right? And using this as our angle, okay, we're going to deal with sine and cosine, all right? And sine and cosine deal with our hypotenuse, and they deal with the opposite or adjacent leg here, all right?
Down from point P.
So if we look at this, once she's completed this triangle here, all right, you're going to notice that obviously this is this is our radius, right? This is our radius, and that's it at 1. That's the definition of our unit circle, all right? this point, since it's located at x, y, now those are the lengths of our legs. All right, this is length x, this is length y. Okay, and again, using our sine and cosine relationships, if we're looking at this angle, sine is opposite over hypotenuse, so y over 1. Y over 1. Cosine is adjacent over hypotenuse, so x over 1. All right, so essentially, we can say that sine of theta is equal to y, right? And cosine of theta is equal to our x coordinate. All right, essentially, that's what we can say because of this relationship here. All right, so then again, we can simplify it down. All right, we can simplify it down. And again, just say that those are our different coordinates. All right, those are our different coordinates. All right, so again, to highlight that last part, sine is our y coordinate, right? Sine is our y coordinate, and cosine is our x coordinate. Okay, and based on knowing these two, right? Tangent is just sine over cosine, so y over x. Cosecant has a relationship to sine, or secant has a relationship to cosine, and cotangent has a relationship to tangent. Okay, so once you understand sine and cosine, the rest of them are pretty simple. It's just that relationship that we should know. Okay. So of course, here looking at these functions, that's what we just talked about here. The key here is understanding that it says when x is not equal to 0, when y is not equal to 0. And again, the reason being, if we have a 0 in our denominator, that makes it an undefined function. Right? It makes it an undefined function. All right, so we have to have it be defined, so we can't have 0 in our denominator. Okay. So then looking here, we can go a little bit further with our trigonomic functions. Again, understanding this point P is at the coordinates x, y, or now as we know it, it's at cosine, comma, sine.
Now you can explore these new definitions by marking some particular points on the unit circle and seeing what the value of each trigonometric function gives you. Remember that the angle in these equations is measured in radians from the rightmost point to the terminal point.
Okay. So again, this right here is 1, 0. Okay, so this should be, it's overlapping, so this should be an angle of 0 radians. Okay, so it should be 0 radians. All right. And again, what this is saying here, essentially it's boiling down to that sine of theta is equal to the y coordinate and cosine of theta is equal to the x coordinate. So since our x coordinate is 1, cosine of 0 is going to be 1. Since our y coordinate is 0, sine of theta equals 0. All right, and again, based on these two functions, we can figure out the rest of the functions here. All right, and again, it is completely okay to say the word undefined, right? Cosecant is undefined because when we take 1 divided by 0, you can't do it, right? So you just say that cosecant is undefined for this specific value here, right? Same thing with cotangent. Tangent is equal to 0. We can't divide by 0, so it's undefined. All right, now if we go up here, okay, this is our 90-degree angle, all right? And again, if this entire thing is 2 pi, right? We said 180 is pi, so half of that is pi over 2. All right, it's pi over 2. Okay, so again, all we're doing here is looking at the x coordinate and looking at the y coordinate and understanding that our x coordinate is cosine, our y coordinate is sine. All right, and again, just plugging in our angle instead of saying theta here. Right, so we say sine of theta is equal to y, so great. Theta is pi over 2, y coordinate is 1, there it is. Same thing with cosine. All right, and again, we follow through with our relationships and we can either define them or undefine them depending on if we have to divide by a 0 or not. Okay, next one, obviously we know this one is pi, right? So this one is pi, and again, so what it's saying is sine of pi is still going to be equal to our y coordinate, which is 0. And now cosine of pi is equal to our x coordinate, which is -1. All right, so this coordinate here is -1, 0. All right, and then this is our 270 degrees, or our 3 pi over 2, right? It's halfway between pi and 2 pi, so 3 pi over 2. Okay, so again, same exact thing. You've got your y coordinate, you've got your x coordinate, you understand the relationships and either calculate or describe it as undefined, depending on, again, dividing by zeros. All right, and so of course then here's our kind of summary table, and hopefully you're going to notice that there is a sort of relationship here with in terms of patterns, right? There's a pattern between 0 and pi degrees, right? So 0 and pi, right, along that line, because it goes 0, 0, 0, 0, undefined, 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 right? It matches those guys up. Same thing with 90 and 270. The zeros both match up, and so do the undefined, right? So you have similar relationships there, okay? Now, obviously, it would be great if we only ever had to deal with those 4 angles, but we have to go beyond just those small ones here. So what happens if we have to find more values?
You are going to continue to build the unit circle by concentrating on the first quadrant. That is the part of the circle where x and y values are positive. To do this, you can use what you know about the ratios of the sides of some special right triangles.
Okay, so again, this is referring to the unit from yesterday. So talking about like our 45, 45, 90 triangle and our 30, 60, 90 triangle. Okay, so we walked through yesterday how to get those different side lengths here. And again, if you don't remember those off the top of your head, absolutely no big deal. I don't either all the time, right? So we'll go through how to recalculate those here. All right. But it's asking where in the unit circle is the terminal point theta for pi over 4? Well, obviously we know pi over 4 is halfway between pi over 2 and 0, right? So it's going to be halfway between there, and that's going to be our 45-degree angle. Okay, so looking at this here, it's asking what would our x and our y coordinates be for this angle of 45 degrees. Okay, so if we can remember that this is 45 degrees here, again, we have our x, our y, and then obviously this value here is 1. Okay, this value here is 1. So what we can do then is we understand that it's a 45, 45, 90 triangle, right? And what we were able to do is we were able to understand that x and y are equal to each other in a 45, 45, 90 triangle. All right, and our c value out here was equal to 1. All right, so when it had us multiplying by c, it's just this square root of 2 over 2. It's just square root of 2 over 2. All right, or 1 over square root of 2, they're the same thing there. Okay, but it's square root of 2 over 2. And again, if you didn't know that, right, all you have to do is redo your Pythagorean theorem. X squared plus y squared equals 1 squared. Again, x and y are the same value, so write them as both that variable a or whatever, right? So you've got a squared plus a squared equals 1 squared. Simplify and solve for a, right? And you're going to get this square root of 2 over 2 value here. Again, understanding this relationship of a 45, 45, 90 triangle. Okay, if we look for pi over 6, all right, so pi over 6, that's talking about if I go from here to here, that's 1/6 of this. All right, that's 1/6 of this. So that's going to be located at exactly about 1/6. So this point here is right there. And now again, of course, to figure out our x and our y coordinates, we have to figure out what kind of triangle this is. So we have to convert pi over 6 into degrees. And we can figure out that's going to be a 30-degree angle. All right. So now again, we're dealing with our 30, 60, 90-degree triangle. Okay, our special 30, 60, 90 triangle. All right. And again, understanding this, okay, we can know that our y value and our x values are going to be square root of 3 over 2 for our x value and 1/2 for our y value, okay? And again, how do we get there? We had to remember that y was 1/2 of x, right? Y was 1/2 of x because this came from, I'm sorry, 1/2 of our c value, right? Because it came from our equilateral triangle, right? And then again, we can resolve this just using our Pythagorean theorem like we did in Unit 1, okay? And then another step further here, pi over 3. Okay, so that's going to be up here. And of course, if we do our conversion, we're going to find out it's a 60-degree triangle. So lo and behold, our x and our y coordinates are going to be similar to the last triangle we just did for 30 degrees. However, the x and the y are now flipped, right? The x and the y are now flipped. Okay, so again, not a whole ton of numbers, just understanding the orders and what they mean, and obviously which is reflective of a 30-degree angle and which is reflective of a 60-degree
Putting
angle.
it all together, you have the coordinate locations of several more terminal points and their corresponding angles. This will allow you to solve some trig equations using their definitions. Take a look at some examples.
Okay, so understanding these ones, we're going to call them our reference angles here. Okay, these are like really good major points that are going to be asked a lot. Okay, so knowing these are just going to be easy because what it's saying is if you're asked cosine of pi over 6, yes, you can plug that into your calculator, but it might give you out a decimal. It might give you out a decimal. And remember, when we're asking for exact values, you can't report them in decimals, right? It's got to be like a square root or a pi, right? So when this is saying cosine of pi over 6, remember, cosine is dealing with our x coordinate. So we go to our angle of pi over 6, right? And we look for our x coordinate. So our x coordinate of pi over 6 is 3 pi over 2, right? So that answer there is going to be 3 pi over 2, right? Same thing, sine of pi over 4. So I go to sine over, or pi over 4. Sine is dealing with my y coordinate. So it's going to be the square root of 2 over 2. All right, finally, it's asking me for cotangent of pi over 3. All right, so cotangent is 1 over tangent, or cosine over sine, right? Cotangent is cosine over sine. So what I can do here is I go to my pi over 3, and I write my cosine over sine, or like saying x over y. I write x over y. There you go, 1/2 over square root of 3 over 2, and I'm left with a value of 1 over square root of 3. All right, so again, I can solve these moderately quickly here if I have my reference angles. And yes, by all means, take a screenshot, save it as a photo. I don't care, right? The more you use this, the more comfortable you're going to be with knowing some of these values kind of off the rather top of your head. Okay, but of course, you should know me by now. I don't want you to memorize anything. Again, it's all about the application piece. So I don't care if you take a picture and save it. Can you apply what you're learning to answer these questions? That's all I want you to be able to do. Okay. And like I just told you, so those angles between 0 and 90 are what we call our reference angles. Okay, they're going to be called our reference angles because we're going to use those as a reference to be able to solve for any other angle, not any other, that's a lie, it's a little exaggeration, but other angles outside of that first quadrant, right? So we're going to be able to look and use those as our reference angles. Okay, so again, looking here, it's a great start. So we can then match, though, these coordinates with the corresponding angles, okay? We're able to match the coordinates with the corresponding angles. And so, again, we said we can solve easily without a calculator, all right? But we haven't looked at any quadrants outside of this first quadrant here. And yes, could there be an easy way to use these ones we've already found? Absolutely, okay? You should know by now that there's going to be a pattern here, all right? So what we can do here is we can consider the different terminal points, right? So this one is 5 pi over 6, and it's in quadrant 2 here, all right? And what would happen is we can make a right-hand triangle with this if we wanted to, and it would look like this here, all right? And the question would be is how does it compare to another angle that we've already found? So again, This is 5 pi over 6, so we can look at how does it relate to something else that's over 6, right? So we look at our reference angle of pi over 6 here. Okay, so if we were to pair these guys up here, you're going to notice that they look the same. They're just flipped across the y-axis. All right, and so what that's going to do is that's going to have the same y coordinate, all right, and the same magnitude for the x coordinate. But obviously now when we're in this quadrant 2, this has to become negative because we'd have to go in the negative direction. All right, so easily what we do is we just use this as our reference, and we understand that since we've gone into this quadrant, this now has to be a negative value. All right, so we can say that pi over 6 is our reference angle for this 5 pi over 6. Okay, and again, the way that I do this is I match them up by their denominators, right? By their denominators. 5 pi over 6, oh, let's go look at pi over 6. All right. Same thing for this one here, okay? And again, the helpful part is matching to the corresponding reference angle that's in quadrant 1, right? That's going to be the trick here. All right, so if I look here, its reference angle is, there we go, hold on. All right, so great. It's got a different reference angle here in case you can use the coordinates. So again, if I reflect across for this example here, okay, we can then notice okay, sorry, apologies. So again, with our reference angle, understanding the relationship between them, and again, if we were to reflect that line across the y-axis and we were to try to make these triangles, we can notice, obviously we can notice here some differences, okay? Or I'm sorry, some similarities. All right. And if we look at another example here outside of the second quadrant, maybe in the third quadrant, okay, this angle is 4 pi over 3. Okay, so we're going to have to use its reference angles here. So using its reference angles, we're going to be dealing with something over 3, right? And if we look at quadrant 1, that's going to be a pi over 3, right? It's going to be our pi over 3 reference angle. Okay. Going to be pi over 3 is our reference angle. And so then we have to notice here that this is positive because it's in this quadrant 1. But we now know that we're in quadrant 3 here. So both of these values here are going to become negative because I had to go to the left and down, right? So both of those values are going to become negative. All right, so I'm going to have my terminal points still be the same values, but again, they're flipping in their sign. So they now become negative. All right. So again, the key with that, of course, is finding the reference angle, right? That's the biggest key, finding the reference angle and then using some logic to figure out, okay, well, what quadrant am I going to be in? Is that typically where the X values and the Y values are positive or negative, or what's the deal? Okay. And again, having this, like this right here would be a perfect screenshot of your relationships and their the reference angles on our unit circle here. Okay, for the sake of time, I'm gonna have you guys solve these, all right? And I mean that one this time. For the sake of time, I'll have you guys solve those as practice problems here, all right? And this is just a quick one I wanna show you. It's a really great example of, okay, look, if I have my different angles, right? If I have my different angles, here are the points, all right? And now if I go over here, it matches up the reference angles. Okay, it matches up those reference angles, and it shows you how it is the reference angle, right? And it changes your X and your Y components if necessary, all right? So obviously the magnitude of this one became negative because now we're in the negative X direction, right? If we go down here, it'll still show you the reflex, like the reflection, right? So their angles are matching up. And obviously now we know in quadrant 4, so we're in the positive X direction, but our negative Y. And then of course, finally, last year we can see how these angles are similar, right? They're similar triangles. And they're going to have the same values, again, just flipping the signs. Okay, so that's a good one for you to play around with there. Okay, and then of course we can relate all of these, since we're dealing with right triangles, we can relate all of them back to the Pythagorean theorem. All right, essentially we can relate them back to Pythagorean theorem. All right, so again, we have this a squared plus b squared equals c squared relationship. And if we understand that sine of theta is equal to y and cosine of theta is equal to x here, okay, we understand that relationship now. Oh.
And connecting the point xy to the x-axis.
Okay. We can then look at these things called the Pythagorean identities. All right, so understanding this relationship and the new relationship we just learned with our unit circle here, we can then do these things called Pythagorean identities.
X-axis, you get a triangle. You also know the lengths of each of the sides of this triangle. If you draw in the line,
We'll try that again.
If you draw in the line connecting the point xy to the x-axis, you get a triangle. You also know the lengths of each of the sides of this triangle.
Okay, here we go. All right. So, of course, we now know that, right? We now know that. And we know our Pythagorean theorem here, so hopefully you can put 2 and 2 together.
Now,
What's going to happen?
what does the Pythagorean theorem tell you when it's applied to this triangle? Plugging in the appropriate trigonometric functions for x and y, you get cosine squared plus sine squared equals 1.
Okay, so again, our relationship of a squared plus b squared equals c squared. So this is our relationship here. Cosine theta squared, sine theta squared equals 1.
This equation represents a very important relationship between sine theta and cosine theta for any real number theta. You will use this equation many times before this pre-calculus course is over. It is also an equation that you will use frequently when you study calculus. So, a word to the wise, learn this relationship.
And I know they said pre-calculus in the video, and they should have said algebra 2. Obviously, this was a concept that we did cover in our pre-calc cast. So again, my pre-calc kids have already seen this. So hey, extra practice. But it is still an algebra 2 concept as well. Okay, but for this year, I just want to point out some notations here. So it says sine squared theta. All right, that's how you could read this, is sine squared theta, cosine squared theta. All right, but essentially what this is meaning is this entire quantity is squared. This entire quantity is squared. And the reason they write it like this is so that you don't get confused between sine, like this entire quantity squared, or just squaring the theta by itself, right? So again, it's a way to make sure that we don't get confused. So if you see it like this, sine squared theta, that means the entire quantity is squared. All right. Now, of course, we have to prove that this is true, like this relationship is true. So again, all we have to do was substitute in like that video said. Again, here's it in words, and we can prove that this relationship holds true. Okay. So then the relationship of any circle is this x squared plus y squared equals r squared. All right, that's the relationship for any circle. All right, when we're with our unit circle, it's specifically this value of a radius 1. Okay, so then if we know our hypotenuse right there, okay, we can then change our coordinates based on this value of r, right? Again, with our unit circle, our r was 1. Okay, so when we were originally looking at it, we were just able to say that sine of theta, it was equal to something, and cosine of theta was equal to something. All right, but essentially we forgot to include that r value because in a unit circle, it just has a radius of 1. All right, so essentially what we can show this as is that cosine is our x value and sine is our y value. And again, both of those are multiplied by our radius. A radius being 1 if it's our unit circle. Okay, so then here you can just plug in the values, all right? And so since this is x squared and y squared here, we have to have all the values and quantities squared here. So if we look here, we have to plug in r cosine for our x. So r gets squared, cosine gets squared. Same thing with r sine. R gets squared, sine gets squared, all right? And that's just a simple replacement there. Okay. And what might we do to get the Pythagorean identity? All we have to do for this one is divide everything by r squared. Okay, if we divide by r squared, this cancels, this turns into a 1 value. All right, so that's all we'd have to do to get to our Pythagorean identity here. All right, and this pretty much wraps up this little unit here. So again, we talked about unit circles, Pythagorean identity. All right, obviously you guys need to make sure you can do this practice. And again, a lot of these are just asking you to use your reference angles. Okay, so have that screenshot that I know that you took, right? Have that handy with you, and then you can use this to help, right? Again, I don't care about you using a tool. I want you to be able to apply what you've learned, all right? Use that tool. All right, so same thing here. Again, this one's asking you to figure out what its reference point is if it's located at this. Okay, so what's that value? All right, and again, it says, what is the reference point? Okay, with the reference point of this. Okay, what is the actual value of 5 pi over 3? So you'd have to find its reference angle, understand that we're dealing with cosine, so what does that mean? Same thing here with sine. So if you've got its xy coordinates, what does that mean for us in terms of sine? Again, for both of these, you can assume we're on a unit circle here. Okay. So then kind of wrapping this guy up. All right, I know we covered a lot of potentially new definitions. All right, but to remind us, trigonomic functions are circular functions because they repeat themselves, and we'll work more on that in later units, obviously. Okay, and then understanding those trigonomic ratios. Okay, they're written here and they're written here. I typed them out, you know, all that stuff. All right, and then remembering that we have our x and our y coordinates can be expressed as cosine and sine. All right, and then based on that, we can figure out the rest of the 6 trigonomic functions on our unit circle. And as we found out, we can also do that for any circle with a radius of r. All right. So then having these major reference point on our unit circle is going to be important. And then obviously those additional reference angles that are within our first quadrant, right? 30, 45, 60, those are some really good values to know. Okay, because again, we can use our reference angles. We can use our reference angles and then be able to easily report out the coordinates for any of those angles along our unit circle here. Okay, so again, we can fill that table in based on our understanding of these reference angles. Okay, based on those understandings and our understanding of these trigonomic ratios. All right, so then last little study here that we'll look at quickly is our Pythagorean identity. All right, and again, x is equal to cosine, sine is equal to y.
If you draw in the line.
Okay, and this is going to be the same video. It's going to show us that if we draw in the line, we can make a triangle, and there's a relationship
Now,
between
what does
that
the Pythag
being cosine and sine. Okay, so this is just recapping that for you. Again, looking at the other approach of actually just solving it, right? So solving it outright using Pythagorean theorem. All right, and then we can do other Pythagorean identities. Understanding this relationship here and how we got there, we can find other Pythagorean identities. So essentially, what this is saying is we're dividing everything by cosine. So if we divide all terms by cosine, we get a 1, okay? 1 over cosine right here is our secant. So 1 over cosine is secant, but we have cosine squared. So this turns into secant squared. All right. And then sine over cosine gives us tangent. So we have tangent squared. So this becomes another Pythagorean identity. Okay, this becomes another Pythagorean identity. All right. If we do the same thing here with sine squared, we divide everything by sine squared. We get our 1 right there. 1 divided by sine is our cosecant. Again, that quantity squared, so does cosecant. And then if I have cosine over sine, that gives me cotangent. Again, both of those are squared, so it's cotangent squared. All right. And again, I guess that's a good reference point or a point here. If they're not both squared, we'd have to talk about how to actually approach that later on. Okay, so both of these are squared, which gives us our cotangent. So that gives us another Pythagorean identity of cotangent squared plus 1 equals cosecant squared. All right. And so again, to kind of summarize this, these are our 3 Pythagorean identities. All right. And we're going to use these later on to help us solve for problems and how to rearrange things. Okay. So this becomes a useful trick here. And again, it all stemmed from figuring out this first one here. It all stemmed from figuring out this first one, which came from our understanding of right triangles and our unit circle, right? That's all that came from. Okay. So of course, here's our summary. Again, another really good image you might want. And again, if you really need the study for this one, it's not super long. It basically just has the Pythagorean identities on it. All right. So that kind of wraps this up here. All right. So then of course the practice is going to cover both of those studies, even though that second one was super, super short. All right. And we have these different points. Okay. It's going to ask us for the reflex angle, figure out the angle based on the points given. What's our reference angle? Okay. What's the value of cosine? What are our coordinates? All of that stuff. Okay. So this one is a little bit longer because it was a brand new concept. So again, take your time with that, at least answer a few of them. Okay. And then for this unit here, we only have the one quiz. Okay. So we have one quiz, and this is of course an extra credit journal opportunity. So if you do this, even partially do it, turn it in, you'll get extra credit points for it. All right. So let me know, or not, you don't have to let me know, I get your grades. But if you want to do that, you can do that. That's extra credit. So right now, officially, we only have these 2 mini quizzes here. All right. And I can try to introduce this lesson here of 5.4 in the next, oh, I know we only have 10 minutes. So I'm not going to do that to you. So let's just pause right there. Okay, so we'll pause, look at my face for a second, realize this is a good stopping point here. Okay, so officially tonight, I am assigning you 5.3 and 5.2. So those 2 lessons that we just covered. Okay, I'm officially assigning those to you. All right, now if I go back to our lesson here, okay, all right, we did not get to cover a couple of these baby lessons here. So not a big deal, right? So what's going to happen is for 5.4, 5, 6, 7, 8, 9, and 10. All right, so kind of, I think 6 units, if I can do math correctly, which, 1, 2, 3, 4, 5, oh, I can't, 7. All right, so there's 7 lessons here. And what I will do is I will make obviously a video lecture for you this weekend, okay? So this is kind of going to be your responsibility to cover for this weekend, all right? And again, I'll post that video as just a normal YouTube video link, okay? So you can jump ahead, you can watch it at your leisure, you can pause, you can, like I said, skip to the part that you need, whatever. Okay, so I will make a video lecture covering all of those lessons. All right, I'll make a video lecture covering all of those lessons there. Okay, and again, as always, you have plenty of time to get this stuff done. All right, again, you know that you only have to do the quizzes for each section. Any practices, any journals, any projects are extra credit. Okay, so only do the quizzes, and then we have our CST here, all right? So essentially, what I think would be a good target for you is if you could finish up Unit 5 by Monday, right? I think that's a really good target for you if you're on track finishing that up by Monday. If you're a little behind, or if you want a relaxed weekend, okay, let me remind you, next week is your solo week, okay? So next week, we have 0 meetings, right? It is literally an entire week for you to be able to work at your own pace, catch up if you need to catch up, refresh yourself, whatever you need. But next week is your week to get caught up and finish this up here on your own, okay? And then quick reminder, once you're done with Unit 5, next week should be dedicated to you working on your semester review and exam. All right. So of course it's going to take you over an overview. It's going to have a lot of review problems. So again, I always suggest that you do this here. Okay. And then you only have this one exam. All right. You only have this one exam. All right. So that will be, of course, again, for you to work on sometime whenever you finish with the entire unit. Okay. So you should be able to finish this up here, right? We should be able to finish up through unit 5 and then start on your semester exam. Okay. And same like last time. Okay. Same like last time. All of that stuff needs to be done by next Friday at 11:59 p.m. So Friday, July 31st, 11:59 p.m. Okay. And of course, what I will do is I will send out a weekend update, obviously this weekend, to let you and your parents know where you're at. And then middle of the week, next week, I'll also send out an additional update, just kind of letting you and your parents know, like, hey, by the way, deadline's coming around. Here's how much you have left, right? So by all means, if you need help, of course, reach out. I'm here for you guys. But other than that, I'm not going to keep you any longer. I know you've got work to do. So this has been wonderful. I appreciate you all showing up every day, your attentiveness and all of your efforts. So let me just remind you, we are so close to the finish line. Okay, we are very, very close. All right, but this is where you need to push through and you need to finish, right? So finish strong here. And then again, as long as you've got that grade of a middle C, 75% or higher, right? You're going to move on and have that program movement. So again, keep that motivation in your head. And other than that, guys, I hope to see you real soon in the fall. Okay. Again, if you got questions, reach out. Other than that, have a great stinking weekend. Let me know. I'll talk to you guys later. Goodbye. Goodbye.